Is it so? You send me a message so I'll know exactly where to get started. Any idea where to get started? Anyone? The browser is starting on the computer. Does take a little bit of time in the morning. As far as I can remember, we already covered process part and then threads part, right? And we are supposed to start IPC. Of course, I have a lot of students from different classes, all from OSG. It's difficult for me to keep track of who was on which page. So just give me a quick
Slide 5 as a price.
thread.
Yes,
Did we?
slide 5.
Okay. So did we finish the thread file, the thread part of the chapter?
Now the slide 5 of the I will type.
Slide 5 of the thread. Is it so? Is that what you mean?
Yes. Yes.
Okay. So slide 5. Can you give me the topic? Do you remember the topic? What exactly was I was talking about
The
on thread
overview.
5?
Overview.
Okay. If you can give me, we can get started right now because otherwise I have to wait. I mean, for my computer. It's getting started, but it does take time. Everything seems very slow in the morning. I don't know. The fifth slide, I think, was it a model or was it implementation? So we talked about the thread benefits, right? We talked about the benefits of what the reason behind introducing this multi-threading concept, which was basically introduced by Java in 1995. In fact, Java championed this idea, and naturally, all the other operating systems they started supporting it. For example, Windows started supporting it from Windows 2000 version, and so on. Okay. Solaris that came from Java. Then we have the Mac. So all of them started supporting this multi-threading concept. So in general, we understand that what are the benefits of threads. Okay. The overview. All right. So the overview, all these things are part of the overviews. The part of the overview, and the part of the overview that we have that we are discussing right here, the benefits and the structure and the model. Okay, so these are some of the things that we were discussing and will be discussing at the beginning. So talking about the benefits, the key benefits that we get from a thread, the reasons we use the thread, the benefits. First one is the speed, and we need, of course, all of us, we want to increase the efficiency of the performance of the software, the program. And one way to do it is to make it multi-threaded. Now, multi-threading is an optional thing. You don't have to mandatorily implement multi-threading. You can, if you don't want to implement multi-threading, you can write a single-threaded program. You're welcome. No problem with that. In fact, most of the programs that you still see are single-threaded. But multi-threading has some real benefits. One of the benefits, as I said, is speed. The next one is resource sharing, because remember, resource is allocated by kernel to a process. A resource is allocated to a kernel by kernel to a process, and kernel doesn't allocate separate resources to different threads. And the threads, if you have multiple threads inside your process, these threads will start sharing that resource that the process holds during its runtime. So resource sharing and resource utilization is better, as we say, and much faster. And in fact, these threads, they will also share all the files and the memory space. Of course, they're sharing the address space of their memory of their parent process. So by sharing all these things from the parent process, the things can be done within themselves, within the process environment, without unnecessarily getting kernel involved. Because remember what we said, the more we involve the operating system, the more we involve the kernel, the chance is the computer or the performance of the program will degrade. So basically, it will slow down, right? So what we get from multi-threading is a huge benefit. One of the key things about threading, that's a common question that rest assured that there will be a question like this in the exam. It's a very common question they ask. Is when we talk about threads, and we understand threads are multiple channels of sequential execution of codes inside their parent process. Okay? So what are the things they share with their parent process, and what are the things they don't share with their parent process? This is a very common question that we have. What do they share? They share the parent process address space. Now we know what is address space, a bunch of logical addresses generated by CPU for any program that wants to run as a process. Now, since these threads are running inside the process, within the process environment, or within the process boundary, so they have no choice but to share their parent processes address space. CPU will not generate separate address spaces for these threads. There's no point doing that. Okay. Now, so that's the first thing they share. What else they share? Another important thing, if you can remember the time when we were converting those static programming codes into an active entity as a process on RAM, we kind of split it up. We did a lot of other things, but we split it up into 2 or 3 parts. We created a stack, we created a code part, a stack part, where basically the part of the codes will be loaded, the part of the codes that are going to get executed, that will be loaded, and it will get executed from the stack part and data part. Now, what the threads share with the threads definitely have their own individual sequence of codes. Okay, but what they share with their parent process is the data part. The data part is the one that they share with their parent process. Okay, that can create some sort of problem that we'll be looking at very soon. especially in IPC, because if there is a shared data, then there could be problems, and the problem that we will discuss is called, it's not a deadlock as such, but it's a problem that we refer to as race condition. Okay, we'll talk about it in a minute. What else will they share? They will also share, as I already mentioned, the resources that has been allocated to that process by the kernel. So naturally, when it comes to sharing, three things: address space, resource, and data. What do they don't share? What are things they don't share with the parent process? That means they have those things on their own. The first, the things that they don't share with a parent process are, first of all, their own codes. Surely they have their own codes. Okay. Number two, they have their stack. Yes, they have their own stack. And because their codes are independent, so their stacks are separate. They have their own stack. What else? They must have their own PC register. PC or program counter. They have their own program counter and a whole bunch of other registers. These are their own registers. Naturally, because these are the things that are directly related to the execution of code. And since codes are separate, then these things must be different for different threads. So these are the things they don't share. Again, the first thing, the codes, then the stack, the PC, and a whole bunch of registers. So these are the things that are unique to individual threads. Okay, I think I can get started in a minute. Almost there. So please remember, that can be a very important question. And as I say, the speed. So that brings us to the next part. That is, what are the benefits? The key benefits, the speed. And you can feel how important that speed thing is from your real-time experience. Like you open a Microsoft Word for the first time, you open Microsoft Word, maybe you want to open a file, and it does take a little bit of time, doesn't it? It does take a little bit of time. You have to wait because the process needs to get loaded, get started, and then the particular file will be accessed. So altogether, it does take a little bit of time. But now, when it is up and running, now you go there and try to open a new tab, a new file, or even another file from within the process environment. So what do we do? We go and click on File and choose New or Open. This time you will see how fast a new window will pop up. And you can open as many windows as you want. Microsoft Windows, Microsoft Word. So what does it mean? That means that you are actually creating threads. You are actually creating threads. This is where multi-threading comes into action. If you compare the first time, the delay in the first time, that you had to wait there, how long you had to wait before things got started, with the speed by which this particular new windows keep moving, keep opening, then definitely you understand that there is an improvement. And that improvement is because of threads. So now at last we are looking at these other things, and as you can see, we talked about the models basically, and we also talked about the benefits. Let's go down. And we talked about the context, why we need it. This is the overview, the quasi-parallel execution. And as I said, I like to use the word the different separate channels of sequential execution of code within the process environment or within the process's address space. Okay, whichever way you want to express it, both are correct. So that is exactly what it is, and they're getting switched. And the thing we need to remember, the all threads inside a process must finish their execution before the process gets switched. So that is one of the important things that we will be learning. That is the thing that we have to understand. The next one that we are going to look at is what we call a model. Now, in this part, we are basically talking about the things to share and the things that don't share, as you can see. And I've already mentioned it. It all comes down to what they share and what they don't share. And now we understand what they share. They share data. Okay. That's the most important thing. They haven't mentioned it right here. In fact, it's true. They share data, and because of that, we also have a little bit of a problem, race condition. They share data. They also share the resources of the parent process, and they share the address space. That these are the three most important things that they share. What they don't share, when it comes not sharing, the things they don't share with their parent process, well, first of all, they must have their own stack because they have their own codes, they have their own stack, and then the register values, including the PC or the program counter. Okay. Program counter and the registers. We sometimes call them mini process, lightweight process, whichever way you want to express it. Because why lightweight process? Because they are so fast. That's why we call them lightweight process. Then we have multi-threading. The multi-threading is about having multiple threads running concurrently, at the same point of time. That is what we call multi-threading. And multi-threading, as I said, is not mandatory. So if you choose to implement multi-threading, it's up to you. Multi-threading, as I said, is an optional concept because not necessarily you have to implement multi-threading. It's up to the programmer and how he wants to write his programs. Okay, that is why neither kernel nor CPU cares about multi-threading. In fact, kernel doesn't want to bother about multi-threading. Okay, so it's up to the process. It's entirely to the process, and that's what it remains. What I mean is, very soon we'll see when it comes to the implementation of this threads, we will see that it is the control is basically in the hand of the process. In the hands of the process or in the user mode, not in the hand of the kernel anymore. So that is what we do. Now the second thing, then we will move on to the benefits. As you can see, we will move on to the benefits and we will try to see that what we can find there. And as you're looking at the benefits, you can clearly see that in the benefits part, the most important thing that stands out is speed. And in fact, it is true that it's all about speed. And that is perhaps one and only benefit. But not the only benefit, definitely not only. Well, we are looking at the model once more, and this is something that we understand. There's nothing new in it. As we see, it is multi-programming and multi-threading, and we have the structure with a stack and a stack on its own, and there are individual implementation of the threads, independent and individual implementation. There's a very interesting observation that we are going to do right here. Now let's finish this part and then we will go to the benefit part. Now what we are looking at is the thing that we are looking at here is a very interesting slide. Of course, it's a familiar one because it is, we already know, a process table, right? It is a process table, or it is a process table, and since it's a process table, we call it a task manager. But one of the interesting things that you can see is the process table. The process table, the task manager. One interesting thing about this task manager is you can see that we remember that a process table, or task manager has the process, all the processes in the rows and the PCBs attached to them. So the PCBs are available. So we can see the PCB very, very well. Yeah. Okay. Well, the PCB that is associated with each process. That we understand. But then, under each process, if you look down, if you expand it, then you can see If it is a multi-threaded process, then all the multiple threads which have been listed right there. But one thing is an interesting observation, that is free. And the thing that we are going to talk about is this empty space there. The threads are there. We understand these are two new threads that are running within that particular process. That's the 32-bit Microsoft PowerPoint. But then the question is, why nothing is there in that space? Why that space is kept empty? What could be the reason for that? To get the answer for it, we'll have to wait a little more. And in the next few slides, I'm referring to these ones. As you can see, this part is missing. So essentially, we have PCB in the process table, but now no TCB. That is thread control block. So where is it? Do we actually have anything called thread control block? And if so, then where is it? Well, it is missing. But however, it seems like the process table just maintains the basic information about how many threads are open at the moment and which thread is probably running at this very moment. That's a little bit of information that we keep stored up. Okay. Now, yeah. So that is exactly what they do. We can see that some of the information is missing at this level. That means that we don't know exactly where these TCB, as we call them, thread control block is. PCB is right here. Okay. There's a reason why TCB is missing in the process table. Look at the next one. If it's a single-threaded program, just by looking at it, you understand that this particular program supports a single thread. And again, information, the detailed information about a thread is missing. That brings us to the next part that we call the benefits. What are the benefits? Now, looking at the benefits, let me highlight the key benefits that we were talking about. Better resource sharing. We already know about that. We talked about it. And number two, overlap I/O and CPU computation 100 times faster. Less time to create new thread than a process. In fact, less time to terminate and less time to switch. Okay, and within the same process, they share the memory and files so that they can communicate with each other without invoking the kernel. And that is where also speed comes in. So the key thing is we try not to involve kernel. In the case of process, however, everything is controlled by the kernel. That's why processes are a little heavier than these threads during their execution. So we understand what are the key benefits, and we must, whatever we do, the next part, we go to the implementation. And when we move to the implementation part, we must ensure that we don't lose these key benefits at any cost. Now, what are the problems? One of the problems that I was talking about when I mentioned that they shared data is a race condition. And that is what they're hinting at. Number of complications. Since the shared data, one thread may read and another may write, and it's the same location, here is needed. Especially whenever there's a dependency. It's not necessarily, the problem is not restricted to thread. It can happen to processes as well. But with the threads, it's more likely because they keep sharing the data and the resources. Okay, so it is more likely. Wherever there are dependencies, involved. What do you mean by dependencies? Is I give you an example. For example, think about it. That this is the data part of a process, and this is the code part. It is a multi-thread program, so we have 3 different threads. Each has its own code and its own stack. Okay. Similar to this and similar to that. There are 3 threads, T1, T2, and T3. Think about it that in the data part, we have a data that's a shared data initiated at 0, a variable x. Now, all these threads, T1, T2, T3, whenever, and they will run sequentially. We know it. They will take turn. Whenever whoever runs, they will do the same calculation, x equals to x plus 1. This x is the value they get from the shared data, like that. So they get this x, and this x will be brought in right there, and then the other things will be calculated. Okay. So we have these x equals to x plus 1. That's the calculation. This x is a shared value or shared data. So now, say for example, T1 runs first. So what will T1 do? T1 will generate a new value of x, and that will be 0 plus 1 is 1. And after it gets to the 1, this 1 must be updated back and saved back into the shared data part. So basically, it goes through a cycle that we call fetch, then execute, and update. So it has to go through a cycle that is called fetch, execute, update cycle, and it must go through it. It must go through it in that particular order. That is what it does. But now think about it, that what will happen if now after T1 has finished its execution, it will be the time for T2 to get started. So they will take turn. T2 will get turn, and T2 will start working on that. So T2 will now get the value that is 1, that is the updated server value of the in the shared data sector. That's the value that they will find, and they will fetch it. So that is x equals to 1. And when they get x equals to 1, then it will do the calculation as 1 plus 1, and the final x value is 2, and 2 will be updated, and then T3 or thread 3 will run, and final value, the final update is 3, because 2 plus 1 plus 2, 2 plus 1 plus 2, 2 plus 1, that means 3. Okay. So the final outcome, if it runs in proper sequence, is expected to be 3. But what will happen if they slightly overlap? What we mean is T1 started running, and then before T1 could actually finish its update to the common data sector, T2 started running. So T2, when it starts its fetch cycle, will basically fetch an old value of x. That means instead of having T2 is supposed to have 1 plus 1, instead of this 1, it will find 0 plus 1 because it started too early. T1 hasn't finished updating the new value into the data. So if it continues, then you'll probably get a strange kind of output. Instead of 3, you will get 2. Okay. So the problem here is, and this is the problem that can happen when there are dependencies. There are 2 factors. First, we are dealing with the shared data, and number 2, there are dependencies. So these 2 things combined, we end up in something that we call race condition. Please remember, because in the next chapter, right at the beginning, in not next chapter, next part in IPC, that's the first thing you'll be looking at, race condition. It's going to happen, as I said, it can happen not only with data, it can happen with resources, it can also happen with processes, but it is less likely because everything regarding processes is being controlled by the kernel, first of all, the OS, and number 2, they don't really share as such, share the same thing. Okay. Now they can. It can happen with them as well, but it's more likely to happen with threads. Little bit of history, if you look at it, that you should see. MS-DOS, the old-fashioned ones, they didn't support. There was no question of threading in those days. In fact, they just ran one program. Unix supported multi-programming, but all these programs were single-threaded programs, right? So it all started with Windows 2000, and as I pointed out, that 1995 was a turning point, okay, in the history of computer science, and especially programming and information technology, because Java was introduced. So with Java in the market, this very quickly, everything changed. Multi-threading was one of the pioneering things that they introduced, along with abstraction. So wherever you go, it's all about abstraction. Now, in the next few slides, we'll be talking about implementation. Just like in the process chapter, we talked about process implementation. And here we're going to talk about thread implementations and how many different ways we are going to implement the threads. In how many different ways we are going to implement the threads. So that is what we are going to look at. There are three ways to do it. So we have the three different modes of implementation. The first mode of implementation is the most welcome one. Why is the most welcome one? Because it is all in the user mode. Everything is getting implemented from the user level, from the user mode. Now, from the user mode, that literally means that in the user mode, if things get implemented from the user mode, one thing we understand, the things must be very fast. The things will be very, very fast because anything that happens without involving the kernel must be very, very fast, right? So that is what we're expecting. Yes, indeed. Everything will be very, very fast. But there will be a problem. As we say, the speed. So implementation from the user mode basically means that we don't share any information. We don't share any information. This is the one. As we say that talking about implementation from the user mode literally means that we are not going to share anything with we are not going to share any information with a kernel. So everything literally should run from the user mode. Now that is fine, no problem. The kernel will never know anything about what a thread is and how many threads are there. So it will not have any perception of that. So the point is that as we understand that we don't share anything with that particular kernel, with a kernel. So basically, kernel doesn't know anything about what is going on.
Mommy.
What is going on right here? Right? It doesn't know anything about it. As we'll see in the next picture, essentially, we have a process table, we have a thread table, but as you can see, the thread table is not shared with the process, with the kernel. The thread table is totally separate. Thread table is in another part. Where is thread table? Thread table is in the hand of the JRE. Thread table is in the hand of the JRE, and the process table is in the hand of the kernel. So basically, the kernel knows nothing about how things get executed. Okay. And thread table is in the hand of the runtime system. That's what we have, a runtime system that keeps track of all the things that's happening inside the thread. But the kernel knows nothing about it. Since kernel knows nothing about it, everything else is fine, that it will run very fast because we need speed. But there will be a problem. And the problem will be when the time comes to get things blocked. When the time comes to get things blocked, that will be the problem. That will be the main problem. So how will we deal with that problem? How to deal with that particular problem? And the problem is a genuine problem, because when it comes to blocking a thread, we understand that threads too want to get switched. But if they want to get switched, then the first thing is, if T1 is running at the moment, T1 needs to get blocked. But how? Now, this blocking is where you have to involve kernel, because remember, blocking literally means taking the CPU back, and only kernel has the power to take the CPU back. So naturally, you have to send a request to the kernel to block thread 1 on the CPU. But now, as we didn't share any information about thread to the kernel will never know what it is. Okay. Kernel will never know what this is all about. The kernel will never know what thread is and which thread wants to get blocked. But kernel knows that there's a special request coming from a particular process, because kernel knows everything about the process, and kernel knows that a particular process is requesting some kind of blocking activity. It's asking it to block something. It's trying to block one of the processes, which the process is asking the CPU asking the kernel to block something in the CPU. Okay.
What's this?
So that is what will happen right in there. Okay. So the problem is, instead of blocking So the point is that we have this genuine problem that instead of blocking a thread, a particular in the entire process will get blocked. So if that problem happens, we have to move on. So what is the solution that we have? As you can see right here, the previous one, instead of blocking the thread, the process will be blocked. That's the problem. So we move on to implementing threads in the kernel mode. If you want to implement threads to the kernel from the kernel mode, threads in the kernel mode, then definitely there you don't have to worry about anything, because now you have basically handed over everything to the kernel. As you can see, GRE is not involved. Everything's still being controlled by the kernel. Everything is still being controlled by the kernel, so the kernel knows exactly who is who and what is going on, and kernel can control it very well. If you hand over the control to the kernel, you really don't have to worry about it, about what is happening. You don't really have to worry about that if you hand it over to the kernel. But then you compromise one important thing. And what do you compromise? You essentially compromise speed. Because we know, and we repeat the same thing again and again, anything that involves kernel will be much slower. So naturally, if you hand over everything to the kernel, then kernel will all the thread operations will become slow and very slow. So that's something that we want to avoid as well, right? We want to avoid that kind of situation, because then there is no point running threads if the kernel switches the threads or controls the threads just the way it controls the process. If there is no performance level benefit, okay, I mean, compared to the process performance, the performance of the process, then there's no point making threads. So it doesn't work as well. So now we move on to hybrid implementation. And that is the most important and interesting thing, and that's the one that we do these days. That's the one we do, the hybrid implementation. Now, what's the hybrid implementation? In the hybrid implementation mode, the most important thing that we have to understand is a part of it. In fact, the scheduling part, switching part, is still being controlled by the user mode with the GRE. And since they're controlling everything right over there, at least 80% of this switching action, since they're controlling those things right at the top level, what is happening is the thread table that we had, or rather the thread table that contained the thread control block, will not be handed over to the kernel. It will stay with the GRE. Okay? But now, as we understood before, that whenever there's a switching involved, we need to block, we need to get in touch with the kernel, because it's the kernel that is responsible to put something on CPU or to block something on CPU. So we need a service from the kernel. And as we need the service from the kernel, we have to get him involved. So we need to keep him informed about what we are doing up there in the GRE level, at the GRE level. And to do that, what we do is we basically drop a thread that we call kernel thread. We drop a thread called kernel thread to keep the kernel informed, or to pass some basic information about the threads to the kernel. I repeat, some basic information. We don't share the thread control block. We just share the who is who. I mean, how many threads are running, how many threads are open, or how many threads are running, and which one is currently working on CPU. So at least that much information kernel needs in the hybrid mode. And that we do by using a special thread which is called kernel thread. Remember this word because you will get some questions. Kernel thread, upcall, pop-up thread. Kernel thread. So the job of the kernel thread is to keep the kernel informed about what's going on related to thread level performance inside the process. Okay? And that is why previously when we were looking at the task manager, what did we see? We saw that PCB, the process control block was there, but the thread control block was not there. The thread control block was not there. Okay? So that was one of the things that we observed at that stage. So that is what hybrid implementation is all about. Now, since we understand hybrid implementation, we'll move on to scheduler activation. So essentially, kernel has a role to play. Now, as I said, from time to time, kernel needs to get involved in it. All the switching decisions, algorithmically, must be controlled from the GRE. So there needs to be a rapid communication between them. Okay. So scheduler activation could be a very complicated process. To keep it simple, we use a technique that whatever kernel does on special request from the user mode, so when it comes for the kernel, to pass the information back to the user mode, it will pass information back to the kernel, back to the user mode. Then naturally, the user mode, if it passes back to the user mode, then it will have to use a mechanism. And the mechanism is what we call upcall. Upcall generally used to be given through kind of message passing, but it doesn't work with the message passing anymore. So we have to introduce another technique. That's what we call pop-up threads. But we'll talk about pop-up threads a little later. The upcall is one that we use. And why do we use the opcall? It is its only purpose is to notify the user level of what it has done. It was supposed to do something, and it has done the job, and it needs to notify it back to them. Okay, so that is what the opcall. So this, when they give the opcall, as you can see right here. Now, in the subsequent slides, they are trying to explain through an example that how it happens. Of course, in this example, they have used two CPUs. These two CPUs, they are how they are getting transferred. Okay, so that is what it all comes down to. At T1, kernel allocates the application to processors. One each processor, the kernel opcalls, and each processor kernel will opcall. And if you go to all the slides, you will just see opcall, opcall, up. So the key takeaway from this part is these three words: opcall, kernel thread, pop-up thread. So we already know kernel thread, we know system call, and now please remember opcall. Opcall is when kernel wants to send a message, an important message, to the user mode, especially related to scheduler activation in the hybrid mode of thread implementation. Yeah? And it does so by using a pop-up thread. As I said, that traditionally used to be done by passing messages, but passing messages is a problem because kernel needs to get an acknowledgement. It needs to know that its important message has been viewed and action will be taken on that. Because kernel, this communication must be based on acknowledgement. So what we can do is now to fire a thread. And that is what we'll be looking at right here. Now this one, these are some of the steps that they have shown. Pop-up threads. What are these pop-up threads? They do ask questions on pop-up threads. Pop-up threads are threads without any history. And in fact, without stack or without anything inside them. Okay. So their sole job is to communicate. In fact, their sole job is to block the user mode, just like our pop-up messages. So the only job that the pop-up threads do, the pop-up threads was simply block the user mode. If I may say that, it's just like a pop-up messages. You are doing something in the browser and suddenly you get a pop-up message. What does it do? It literally blocks you. It stops you from doing anything. Okay. It blocks you, and your window freezes. Your browser freezes. You can't move forward unless you kill it. Now, when you kill it, there's the same thing that happens. The user mode or the GRE was probably busy doing something else, and suddenly it gets a pop-up message. It must kill it to move forward. And as it kills the thread, kills the pop-up thread at the user level, the user space level, it essentially sends an acknowledgement back to the kernel that its message has been queued. So the job has been performed. The task that you GRE, the runtime environment, the user space assigned to the kernel. Kernel has done it. Now it is time for them to do something else. That means to decide which is the next process, which is the next thread that will be scheduled on CPU. So essentially, that is how it all runs. The latency between message arrival and the start of processing can be made very short. There are lots of benefits because of which we use the pop-up thread. The most important thing is acknowledgement. Okay, so that brings us to the end of this thread part. In short, the things that we studied. What is a thread? The thread model, essentially talking about what they share with their parent process and what they have on their own. Then what are the key benefits? Why do we implement multi-threading? And then we talk a little bit about the implementation, the 3 different ways that we can implement them. And each of them has its positives and negatives. And the most common one that we follow today is the hybrid implementation, where 80% of the operation, literally much of this control is in the hand of the user mode, the GRE, but it still needs the service of the kernel. And how kernel gets involved. Okay. Through kernel threads, we engage kernel, we keep kernel informed about what is happening, right there. And on the other hand, we kernel, whenever it needs to do some task, it will simply use an up call to get back to us and tell us what to do. So these are the ways that we work on hybrid mode, a very important part. Then towards the end of the hybrid mode, we talked about how kernel plays an important role in activating the scheduler. Remember, it's just activating the scheduler. We are not talking about kernel plays a role in active scheduling. Okay, they don't play a role directly in scheduling, in active scheduling, but it activates the scheduler. Now, then once that module, the scheduler module, get activated, only then the threads will get scheduled on their own way. So these are the things that we studied right in here. If you have any questions, and for that we use 3 important words you must pay attention to. One is kernel thread, one is upcall, and one is pop-up thread. In fact, upcall is the most common way that kernel communicates back to the user mode, and every time it finishes a task, and to get an acknowledgement, an immediate acknowledgement from the user mode, it uses the pop-up thread to give an upcall. Okay, that is it. And kernel thread comes from the user mode to the kernel to keep kernel informed about which particular thread is currently running or has been currently scheduled. So to pass the basic information. After this part, we will move on to the next part, which is basically IPC. inter-process communication. Inter-process communication. Okay. Give me a minute and let me start it. Of course, you don't have much time, but we will get started nevertheless. Inter-process communication. Inter-process communication. IPC. Why do we need it? We need it, or rather the processes need it, as the name suggests, it is two processes communicating with each other, or multiple processes communicating with each other. They need it just to stay safe. It's not to run into a conflict, as they keep running or executing on the RAM, and that it remains constantly sharing resources between them. So that is something, that's the reason behind this IPC. As we said elsewhere, and we will repeat, that basically there are two scenarios inside your computer. Well, first of all, computer is all about resources and processes. The scenario one is what we call the request scenario. In the request scenario, one process can ask for multiple resources at the same time. And at the same time, one resource can be requested by multiple processes. So there you are. It's a kind of many-to-many relationship. So anyone, literally, at any point of time, any process can ask for any resource. Okay. But then these resources will be allocated. Now, these requests that we are talking about, the request goes to the kernel. And kernel, kind of a resource manager, its job is to allocate the resource. Now remember, there's a slight difference, so we'll elaborate on that in chapter 6. Allocation and acquisition are two different words. Okay? Allocation means it's a logical thing on pen and papers. And acquisition, or actually acquiring that particular resource, is a physical thing. Okay? So now those resources, whenever a kernel gets a request from a process for a particular resource, it will simply allocate that resource to that particular process. But then the process will have to wait, because in our second scenario that I just now mentioned, there are two scenarios. One is a request scenario, and one is a usage scenario. In the usage scenario, it is only one process that can use one resource at a time. So one resource can be used by one process only. If even by mistake, two processes vying for the same resource steps into the same resource at the same point of time, there will be a deadlock. The computer will hang, will stop working. Your resource, I say computer, that is basically the resource that will stop working, or in fact, we start calling it blocked. So that resource will get blocked indefinitely. So how can we, what can we do to overcome this situation? Now, of course, kernel is the manager, so we can go back to the kernel and ask kernel to take care of all these things. Well, kernel is trying on its own, trying to implement some general rules as far as kernel can do, whatever kernel can do, to keep these processes safe and keep these resources safe from each other. But that's something that we'll study in the deadlock chapter. But apart from that, to keep things running steadily at a considerably high speed, we need to find something where kernel will not get involved. Because we know involving kernel at every stage means it will slow down the speed, the performance. So we have a mechanism here that is called inter-process communication. A mechanism, an inter-process communication, where the two processes trying to acquire a particular resource constantly keep sharing some information among them. So in fact, they do it by using a number of signaling systems, just like you guys do when you drive a motorbike on the street. You stay safe 364 days a year because you are using some signals, like your horns, the front light, the rear light, the two indicators on both sides. You are using them judicially to communicate something to the other passing vehicles, which are kind of like crisscrossing you on the public street. And they too are using their signals, which you are reading constantly, to stay safe without compromising on your speed. And that's exactly what is happening inside IPC. That's why we need IPC, what we call inter-process communication. Because sometimes if it fails, there's no choice. You have to, just like you run into a deadlock, you run into a traffic jam, or there's an accident, then the policeman should step in. And just like if IPC fails, the kernel will have to step in to resolve that matter. Okay, so that thing we will talk about in the last part. So let's see what else we have. And you'll see that we will start first the review part. We'll just skip through it. Threads. The very first thing that you are looking at is race condition. Right. The very first thing that you are looking at is race condition. Race condition, just now we talked about race condition in our threads class, and you already know what it is. It happens, as you will find right here. I will quickly move into that part, and of course we will get started again. Whenever there's a dependency, as you can see, proper sequencing when dependencies are present. So think about the example that we explained. Also, try to read these examples that they have given. Think about right here. A process, there are two processes, process A and process B. So what process A does is basically there's some computational activities and generates a particular output. Once the output, say it calculates the value of y. And once the value of y has been calculated, then this value will be passed to program B. And what the program B will do is simply to print it. That's what it does. So program A generates a value which program B is supposed to print. So there's a dependency there. And since there's a dependency, if you want to get the proper output from the printer, then you must apply proper sequencing. If suddenly they overlap, for example, program B started running a fraction before program A actually could update the value of Y, then what will happen? Will there be a traffic jam? Will there be a deadlock? No, there won't be a deadlock. The program will still run to completion. Something will still come out from the printer. But if you go there and look at the value of Y, it must be an old value of Y that is getting printed out. Because this time, program B ran a fraction little too early before program A would actually finish its task. That is what we call race condition. Remember, race condition is not a deadlock. Race condition, as we will see right here, race condition leaves the final state of the resource as unpredictable and inconsistent. Okay? All right, we will leave you here. So we'll just take a quick attendance. And in the next class, we will continue with inter-process communication, a very important part. Inter-process communication. We will get started right from the beginning, no problem. Just remind me. Okay, there we are. Xuan Huang. I'm taking your attendance. So please respond. Xuan Huang out there. Chi Kang.
Yes.
Vin Phuc.
Yes.
Yes.
Duc Huang.
Yes.
Yes.
Luong Ha.
Yes.
Tu Huang.
Yes.
Dan Hong.
Yes.
What happened to my browser? Okay. It's not moving. Not Fat.
Yes.
Din Min.
Yes.
Quoc Huy.
Yes.
Huayan.
Yes.
Kim Thak. Kim Thak. Nhật Min.
Yes.
Hiền Phúc.
Yes.
Quang Huy.
Yes.
Minh Khuông. Minh Khuông. Truy Bao. Truy Bao.
Yes.
Huy Min. Lam Chuk.
Yes.
Quoc Hung.
Yes.
Okay, did anyone send me message or anything? No. All right. Just a quick one. Minh Khuông. Kim Thak.
Yes, yes.
Xuan Huang.
Yes, teacher.
Xuan Huang.
Yes.
Wake up. All right. And Kim Thak.
Yes.
Okay. And Min Kwong? All right. Thank you. We'll see you again on Monday.
See you again. Have a